Right now, somewhere in the Milky Way, a star is dying. Not slowly, not peacefully. It is collapsing inward at a quarter of the speed of light, crushing millions of kilometers of stellar material into a space smaller than a city. And in the final fraction of a second before it vanishes from the observable universe, it creates something so extreme that the laws of physics as you know them stop working. It creates a black hole. You have heard the word. You have seen the swirling images, the orange rings, the dark circle that seems to devour everything. But the real story of what a black hole is, how it forms, and what would happen if you fell into one is stranger than any image you have ever seen. Start with the star. Picture the sun. That nuclear furnace 1.3 million kilometers across, fusing 600 million tons of hydrogen every single second. It has been doing this for 4.6 billion years. It will keep doing it for another 5 billion. The reason it does not collapse under its own weight is the fusion itself. Every second, energy from those reactions pushes outward, gravity pulls inward, and the two cancel. Astronomers call this balance, hydrostatic equilibrium. It is the invisible tug-of-war that keeps every star alive. Now imagine a star roughly 20 times the mass of the sun. These stars burn faster and hotter. Where your sun will live for 10 billion years, a star like this might last only 10 million. It burns through its hydrogen at an extreme rate, then begins fusing helium, then carbon, then neon, then oxygen, then silicon, building heavier elements in layers like an onion, but the chain has a final stop. When the core reaches iron, the fusion ends. Iron does not release energy when it fuses, it absorbs it. The moment that iron core reaches roughly 1.4 solar masses, a threshold the Indian-American physicist Subramanian Chandrasekhar calculated in 1930, the outward pressure vanishes. The tug-of-war ends, gravity wins, everything falls. The collapse takes less than a second. The outer layers of the star, which moments before extended hundreds of millions of kilometers into space, come crashing inward at roughly 70,000 kilometers per second. That is almost a quarter of the speed of light. When the infalling matter hits the now incredibly dense core, it bounces, sending a shockwave outward. That shockwave is a supernova. In 10 seconds, it releases more energy than the sun will emit in its entire 10 billion year lifetime. For a few weeks, one dying star can outshine an entire galaxy. But what matters is what is left behind. What you end up with depends on how massive the original star was. Stars between 8 and 20 times the mass of the sun usually leave behind a neutron star, a ball of matter so dense that a single teaspoon would weigh about 1 billion tons. Electrons and protons have been crushed together into neutrons, and the whole object is essentially one atomic nucleus, about 20 kilometers across. They are the densest visible things in the universe. For stars above roughly 25 solar masses, even neutron pressure cannot stop the collapse. The core keeps compressing past the neutron star threshold into a singularity, a point of infinite density where space-time curves without limit. Around that singularity is a boundary in space, and once you cross it, nothing can escape. Not light, not information, not any force in the known universe. That boundary is the event horizon. The singularity and the event horizon together are what we call a black hole. Here is where it gets strange. You might picture a black hole as a cosmic vacuum cleaner, sucking nearby objects into its depths. That is not how gravity works. If you replaced the sun with a black hole of the same mass, the planets would keep orbiting in exactly the same paths. The Earth would not be pulled in. Nothing would change, except there would be no light. Black holes do not reach out and grab. They curve space-time so severely that anything crossing the event horizon is on a one-way path. So what would it feel like to fall in? The answer depends entirely on where you are standing. Imagine watching a friend fall toward a black hole from a safe distance. Something extraordinary happens. As your friend approaches the event horizon, you see them slow down. The light reaching you from their body gets stretched by the gravitational field, a phenomenon called gravitational redshift, predicted by Albert Einstein in his 1915 theory of general relativity. Your friend appears to freeze, fading and reddening until they seem to hang motionless at the edge. From your perspective, they never cross. From your friend's perspective, nothing unusual happens at the moment of crossing. No wall, no alarm, no sensation of passing through anything. They cross the event horizon and, depending on how massive the black hole is, they can still see stars, still think, still feel time moving forward. What ends the journey is not the event horizon, but the singularity. There, the difference in gravitational pull between your head and your feet becomes so extreme that you are stretched into a thin stream of particles. Physicists call this spaghettification. We know almost nothing about what happens at or near the singularity because the math breaks down. General relativity stops being able to describe it. Quantum mechanics stops being able to describe it. The singularity is not so much a place as a sign that the current theories are incomplete. It is one of the biggest unsolved problems in physics. In 1974, Stephen Hawking found something that made the mystery stranger. Combining quantum mechanics with general relativity, he calculated that black holes are not entirely black. They emit a faint radiation from just outside the event horizon, produced by quantum fluctuations in the vacuum of space. It is now called Hawking radiation. It implies that over enormous timescales, black holes slowly lose mass, shrink, and eventually evaporate. That raises a hard question. What happens to all the information that fell in? Information in the physics sense means the quantum state of every particle that ever crossed the event horizon. Quantum mechanics says information can never truly be destroyed, but if a black hole evaporates and disappears, where did it all go? This is the black hole information paradox. It is still debated today, with contributions from Hawking, Juan Maldacena, Leonard Susskind, and dozens of others, and still no agreed answer. In April 2019, you got your first direct image of a black hole. The Event Horizon Telescope, a network of radio observatories spanning the entire planet, captured a photograph of the supermassive black hole at the center of the galaxy M87, an object 6.5 billion times the mass of the Sun. The orange ring and dark center in that image were not an artist's impression. They were real data, confirming what the mathematics had predicted for over a century. Your own galaxy has one too. Sagittarius A star, the supermassive black hole at the center of the Milky Way, is about 4 million times the mass of the Sun. It sits 26,000 light-years away, warping space-time at the center of everything you see when you look up at night. Every atom in your body was forged in the heart of a dying star. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now. These elements were made in those nuclear furnaces that burned for millions of years, then exploded in the same supernovae that can leave black holes behind. You are made of the material that was not swallowed. You are the debris field of stellar death. The universe is not cold and empty with the occasional dramatic event. It is one continuous process. Stars are born, burn, collapse, and seed the next generation of matter. The matter that eventually became you, looking up at a sky full of light from stars that may already be dead. Right now, somewhere in the Milky Way, a star is dying, and out of that death, everything new begins.